Welcome to This Explainer. Seriously, just take a second and think about the staggering scale of our modern digital world. From the smartphones sitting in your pocket and massive data centers to autonomous vehicles and industrial robots, digital electronics are absolutely the foundation of today's technology. But underneath all of that incredibly complex glowing circuitry lies a surprisingly elegant secret. It's a crazy question, right? I mean, how exactly do simple ones and zeros actually power something as mind-bogglingly complex as artificial intelligence or massive global communication networks? Well, the fascinating truth is that all of this modern complexity speaks an incredibly simple underlying language. The entire digital revolution wasn't built on some complex alphabet, but actually on the most fundamental of choices. And that brings us to the core concept of binary logic. See, digital systems process information using just two states. We call them 0 and 1, false and true, or a low and high electrical voltage. In the kinds of circuits we'll be looking at today, 0 volts represents false and 5 volts represents true. These simple binary states are the absolute bedrock foundation of computing. So, here's our roadmap for today. We'll start with our digital world foundation, look at transistors as electronic switches, cover the basic NOT, AND, and OR gates, dive into universal NAND and NOR gates, and wrap up with building the modern computer. All right, part 1, our digital world foundation. Okay, take a look at this. This is the PN2222 bipolar junction transistor. It's essentially the fundamental building block of digital electronics. Notice its 3 pins here: the emitter, the base, and the collector. You can kind of think of it like a tiny electronic valve. A really small current flowing through that base pin actually controls a much larger current flowing between the collector and the emitter. Moving right along to section 2, transistors as electronic switches. Now sure, transistors can totally be used as analog amplifiers, but in the digital logic world, we just need them to act as simple on or off switches. If you take a single transistor and wire it up with some resistors, you create an inverter circuit. Basically, by applying a high or low voltage to the input, we control the transistor's state, and that dictates the output. This exact wiring setup literally bridges the gap between a physical object and an abstract logical concept. Which brings us to section 3, basic NOT, AND, and OR gates. So how do we jump from a physical switch to actual logical decisions? Well, we combine those transistors to build logic gates. The absolute simplest one is the NOT gate, also known as an inverter. Its rule is beautifully straightforward. It just reverses the input. If the input is a high voltage, or true, the output flips to a low voltage, or false. Simple as that. And to map all these decisions out, engineers use what we call truth tables. Think of them as the literal blueprints for digital logic. They map out every single possible input and the resulting output. For the NOT gate, an input of 0 gives you an output of 1. An input of 1 gives you an output of 0. It perfectly represents that physical inverter circuit in action. Now, let's step it up to a gate with 2 inputs, the AND gate. This one has a super strict requirement. It only produces a true output when literally all of its inputs are true. Think of it like a high-security safety deposit box that requires 2 completely different keys to be turned at the exact same time. Looking at its logical blueprint here, you can see inputs A and B absolutely must both be a 1 for output Y to be a 1. If there's even a single 0 anywhere on that input side, boom, automatic 0 on the output. It's an uncompromising all-or-nothing kind of deal. Now, contrast that strictness with the OR gate. The OR gate is way more forgiving. It spits out a true output whenever at least one input is true. So if either input A or input B or even both are true, the gate just waves the signal right on through. The big takeaway from this table is just the sheer abundance of true states. A 0 and a 1, that gives you a 1. A 1 and a 0 gives you a 1. And 2 1s yield a 1. Literally any true input guarantees a true output. The only possible way to get a false output is if both inputs are completely dead. All right, moving to section 4, universal NAND and NOR gates. So NOT, AND, and OR are great for getting the concepts down, but real-world engineers rely on an absolute game-changer trick to build computers, the NAND gate. It is literally just an AND gate immediately followed by a NOT operation. But what makes it so incredibly special is that it's a universal gate. If you wire enough of them together, you can recreate the function of literally any other gate. You could theoretically build a massive modern processor out of absolutely nothing but NAND gates. If you look at the logic, the NAND gate is exactly inverted compared to that standard AND gate we looked at earlier. Instead of outputting a 1 only when both inputs are true, the NAND gate outputs 0 only when both inputs are true. Every other combination, that results in a 1. And you can see this difference beautifully illustrated in the standard circuit shorthand. Notice the normal AND gate symbol and compare it to the NAND gate right beside it. See that tiny little circle on the output side? That is the vital shorthand that transforms an AND into a NAND. It physically represents that built-in inversion. Okay, just like the AND gate has a universal counterpart, so does the OR gate. Enter the NOR gate. This combines an OR operation right into a NOT operation, and much like the NAND gate, it is a universal building block fully capable of creating any digital circuit all on its own. As you'd probably guess, the NOR logic is the exact opposite of the OR gate. It only outputs a logic 1 when both inputs are dead false. If there is a 1 anywhere on the input side, the output immediately snaps to a 0. And finally, Section 5, Building the Modern Computer. Okay, so now that we've got our logical alphabet, it's time to scale up, and I mean rapidly. By combining simple integrated circuit chips, which, by the way, usually contain just a handful of these microscopic logic gates, you can quickly form really complex networks on physical breadboards. This is exactly how engineers create arithmetic circuits that add and subtract, multiplexers that route data around, and memory units that can actually remember past states. To really wrap your head around modern microprocessors, you kind of have to take that messy breadboard and just multiply it exponentially. Seriously, a modern CPU, which is often smaller than a postage stamp, contains literally billions of these interconnected transistors. They act as invisible logic gates, firing millions of times a second, but all relying on the exact same fundamental logic principles we just explored. Because at the end of the day, every single computer program, video game, website, and wildly complex AI system ultimately depends on these exact simple logic gates. Whether a machine is rendering a massive digital universe or solving impossible algorithms, the whole shebang just boils down to true or false. Understanding these gates, that's your very first step toward mastering digital electronics. So I want to leave you with this thought. The next time you pick up your phone, ask yourself, how many billions of microscopic logic gates are quietly making decisions in the palm of your hand right at this very second?